ended last Wednesday by taking a look at these two molecules and trying to figure out which atom was the most acidic. Okay? So to figure out our most acidic hydrogen, first thing we'd want to do is find all our hydrogens. As we push through with future drawings, you'll stop seeing hydrogens drawn on, and we'll talk about one of those reasons. So in this case, I tried to be nice and show all of the hydrogens, so you could then try and start to evaluate and decide which of these is the most or least acidic. Okay? Let's pick the structure on the right to start with, because I think that'll be a little bit easier to work with. We want to identify all of our different hydrogens. Okay, so where do we have different hydrogens within that structure?
Hydrogen bonding.
It's not hydrogen bonding. Okay, we could look at the ability for this compound to hydrogen bond, but that's not what the question's asking. All we're looking for here is different hydrogens. So what would make a hydrogen different?
What it's bonded to.
What it's bonded to. So we could go through and start to identify our different hydrogens. We have a whole bunch of hydrogens attached to carbons, and we also have a hydrogen attached to an oxygen. All of those hydrogens that are attached to carbons, are they different? Okay, at least as a first pass, no, they aren't different. It turns out that that guy is also going to be slightly, eventually it'll draw, there it goes, different than the others, but the rest of them are all pretty much the same. Okay? So we've identified three types of hydrogen, if you will. Okay? Now what we want to do is look at those three types and see which of those would be potentially the most acidic. Okay, well, what's our definition for an acid? A hydrogen ion donor or a proton donor. That means this molecule needs to give up H+. Okay? So the atoms that are connected to that hydrogen need to take the electrons away from the hydrogen, because the hydrogen right now is currently neutral. Which atom is better suited to take the electrons away from hydrogen? The oxygen is going to be a much better option. Why is the oxygen a better option than our carbons? It's more electronegative, so it's already pulling that electron density away. So when we go through and look at that structure, we should hopefully be able to eliminate our carbon hydrogen, which should erase here in just a second, or two or three. There they go, slowly. So really what we're concerned about for our acidic hydrogen is that one on the oxygen. Okay, so in future classes, when we go through and ask for the most acidic hydrogen, you'll notice that I won't have the entire structure drawn out with all of the hydrogens shown, okay, particularly to the carbons. Why not? What's the reactivity of those hydrogens attached to those carbons? Very, very low. Why? The difference in electronegativity between those two atoms is virtually nothing, which means we don't generate partial charges, which means we minimize that reactivity. So if we looked at this question in the future, that structure would probably get drawn out, in theory, a little bit nicer looking than that. Something along those lines. Okay. One quick note. Where's the hydrogen aimed in the one I just drew? Up or down? Where's the hydrogen aimed in the one that was drawn nicely? What's the difference between those? Rotated is the right idea. Is there a difference in energy between these? No. Okay. So this is something you have to be careful with when looking at organic structures. Where is up in our real world? Anybody point to the up direction? Straight up, relatively simple, right? Where's the up world when we look at organic chemistry? Every direction is up. Every direction is down. Every direction is left and right. It is very difficult to go through and actually specify. One of the things that's going to make this further difficult is that we have to realize that the kinds of bonds that we're dealing with in a lot of structures, go through, let's try orange. I think that orange stands out. If we take a look at that orange bond, what type of bond is that? It's It's a sigma bond. If it was a pi bond, we'd see two lines. Okay, what's special about sigma bonds? They can freely rotate. So that hydrogen can be aimed up or down, and there's no difference in the overall structure. The example I like to give, which may be a bit testy for most of you, let's see what happens. What's my name? How about now? Now? It's different. How about if I do this? No, it's still the same. I'm still the exact same person, even though you're seeing something slightly different. We can flip, rotate, and spin. I won't stand on my head. I'm still going to be the same person. Molecules are going to do the same thing for us. Okay, so we have to watch out for those sigma bonds. So, you happy identifying that hydrogen is the most acidic in the rightmost structure? Okay, how about the leftmost structure? We would again try and go through and identify all our different hydrogens. Okay, hopefully you can identify those three again, okay, as being significantly different than all of the others. Of those, which one's the most acidic? The one connected to the oxygen, because electronegativity. So what we've now identified between these two structures is the most acidic hydrogen on each one. Okay, the question then asks, which is the most acidic hydrogen between the two? Okay, so left or right? Well, the analysis that we've gone through so far is just looking at what the atom, where our hydrogen was connected, what that atom is. Okay, well, in both cases, it's an oxygen. What does that mean? There isn't a difference. So if we don't find a difference, what should we do? Move to the next atom and look for a difference. What's the next atom? Carbon. So I'll go through and color them both in purple. All right, depending on how refined we wanted to get with this. Is there a difference between those two carbons?
Yes.
Yes, what's that difference? sp2 hybridized versus sp3. What else changes when we change our hybridization? Electronegativity. The less hybridized we are, the less p character, the lower in energy our orbital becomes, which means it holds the electrons a little bit tighter to the nucleus. Which means when we look at the sp2 hybrid orbital, or hybrid carbon, it is actually more electronegative than our sp3. How does that affect our hydrogen out there?
Well, the oxygen has less electrons close to it, so it's kind of
Our leftmost carbon is drawing effectively more electron density away from that oxygen. Well, if it's that oxygen's losing electrons, what's it going to do? It's going to steal them from its next most available source, which is going to be that hydrogen. If we take all the electrons away from that hydrogen, what do we have floating out there? A proton. There's our acid. Okay? So what we went through and did in this attempt was look at a couple different comparisons. We start by looking at our atom effects. What's the energy of that atom? Okay, what's its electronegativity? We can then push that further. If we don't see a difference, move one atom further away and go through that exact same kind of comparison. What if you didn't see that hybridization effect? That is admittedly a very tricky effect to look at. Okay, is there something else we could have evaluated? What's the next atom furthest away? We're either jumping to an oxygen or carbon versus carbon, or hydrogen. Is there a substantial difference between oxygen, carbon, and hydrogen? Yeah, what's our difference? Oxygen is way more electronegative. So what ends up happening is that oxygen steals electron density much more so than our carbon or our hydrogen in the other molecule. Well, if it steals electrons from that carbon, where does that carbon then steal electrons from? Our oxygen. And again, we end up weakening that bond. We shuttle most of that electron density into the structure, away from the hydrogen. It's again more acidic. Yes?
Can you explain again how the effect of the double bond?
The which?
Double bond, the
Did not talk about the double bond at all.
No, sorry, the sp2 versus sp3.
sp2 means we have less p character. What's the difference between our p and s orbitals? Where are they held? Your p orbitals are a little bit further away from the nucleus. So if we have more s character, we're holding electrons tighter. How do we define an atom's ability to hold electrons? It's electronegativity. If we move to the sp2 hybrid orbital, our electrons are held tighter to the nucleus. We're looking at a more electronegative atom. If that's more electronegative, it's going to do exactly what's happening here. It's drawing electron density away from that hydrogen, making it more acidic.
Just
Right.
looking at the complex functional group that it's a carboxylic acid.
Was there another way to answer this question? Absolutely. Okay, we can circle our acidic hydrogens again in both cases. We could push this a little bit further. Maybe you're really good with your nomenclature. Some cases that'll help you out, some cases it won't. This happens to be one of those cases where it helps you out. What functional group do we have here? Actually, I lied. Don't answer that one yet. What functional group do we have over here?
Carboxylic acid.
There's a couple answers we can come up with that. You might see it referred to as hydroxy. Prefer to not reference it as hydroxy because that's just referring to the OH bond. If we push that out to that extra carbon, what functional group are we looking at? It's an alcohol. Okay. Now we shift to our leftmost structure. What functional group are we looking at in that situation? A carboxylic. What was that last part of it? Acid. Which do you think is more acidic, the acid or the alcohol? Sometimes nomenclature helps you out. Not always, but sometimes. Okay? So yeah, variety of ways that we can go through and approach this. Why do we end up calling the carboxylic acid an acid? Because that hydroxy group, that hydrogen, becomes so much more acidic that we refer to it as an acid. That's where the name came from. It's actually based on the reactivity of that hydrogen. Okay? So, what we're trying to go through and do is minimize that charge. Okay? So, a lot of our reactions are going to be centered around that. How do we minimize the overall charge? And we did that in this case as well. What we were looking at is the ability of the atom where the hydrogen was attached to hold on to those electrons, which effectively means it's reducing the overall charge. Because if it can't minimize that charge, it's spitting those electrons back onto the hydrogen. Okay? Questions about that? All right, can it get more complicated? Absolutely. And with this example, we went through and looked at what I would argue is an inductive effect. The ability of other atoms to withdraw electron density. We could also look at a resonance effect. Very, very similar to induction. And we'll look at an example of that hopefully in just a little bit. Okay? So, when ranking acidity, it's always concerned about stability. Right? Minimize that charge as much as possible. Place the charge on an atom that can hold it better. So if we're trying to rank our acids, we want to look at the conjugate base. Okay, so we don't want to draw in a bunch of structures. Let's come up with a symbol to represent our acid. It's a good symbol for an acid. Okay. General good one would be A for acid. What does our acid need to do? Donate a proton, also known as a hydrogen ion. So if our acid is actually going to be valid, we need to have that hydrogen present as well. If it's going to act as an acid, what's it going to do? It's going to give up the H+, and we'd be left with A-. Okay. What if this was a strong acid? What happens? Fully dissociates into H+ and A-. What if it's a weak acid? It only does it partially, which means we've got a reverse reaction associated with that. It could go backwards. So when we try and rank our acids, ultimately what we're doing is looking at this expression for every single hydrogen that we have within our structure. and we start to make simplifications within those rules. Is there something that expresses the ability mathematically for HA to give up that hydrogen? We're looking at a K expression, K for our equilibrium constant. We can refer to it as our Ka because it's our constant for our acid, which is our products over our reactants. Right? So if it's a strong acid, what happens to the size of Ka? Gets really, really, really big. Okay? If it's a weak acid, Ka is relatively small. Pretty much everything that we're going to be dealing with this semester is dealing with Kas that are in that small range. Very rarely do we see our strong acids. Typically, the only reason we introduce our strong acids is when we really want to push and get out of an equilibrium situation. Okay? So it happens kind of rarely, but we will see those strong acids evaluate. If we're going to look at kind of our definitions, minimizing the charge. So now what we're going to do is instead of looking at these numbers, because how do we figure out the Ka for any acid? The chart is ultimately the right idea with this. We would have to go through an experiment, determine the concentration of H+, the concentration of our conjugate base, and the concentration of our starting acid. Okay? Then we set it up into this equation. We generate our Ka. Okay? You guys did this in 152. To figure out the Ka for a single acid, you had to go through and run a long experiment. Okay? Took days and then a couple days to go through and process that data as well. Okay? That's a bit tedious. So what we do instead is look at big tables and charts. So we could go through and quantify everything based on those tables and charts. Okay? Or what we could go through and do is come up with ways that we could approximate these things and get through to our answer as quickly as possible. Okay? So to do that, what we want to do instead is evaluate our structure. So we can step away from the mathematics and come up with a way to look at our structures in this case. So let's draw in another acid. Let's call it HA, and I'm going to go 2, just to say it's a different acid. You were all looking down, apparently, or didn't find that funny. Okay. Which of these is the stronger acid? Should be a hard question. But we need to know something about what's happening in these cases. We could go through and look up the Kas for these, but we don't have that information. So what we want to go through and do is look at our structures. Okay, where do we see big differences? That 2 just means it's A, not 1. Okay, it doesn't mean there's 2 A's. Different on what our hydrogen is attached to, but when we look at those, are those charged? So if we take a look at the reactants, do we see any charge? No. And according to our rules for ranking acidity, what do we want to do? Minimize charge. Well, if there's no charge to minimize, that's going to be a really crappy place to look to try and figure out which one's the stronger acid. So let's look at the product side. Which of our products should we look at? Product number 1 or product number 2? Why 2? Yeah. Why 2? It's the only thing that's different. Better? Good enough? Okay. Number 1, they're both H+. That charge isn't going to change. It's always going to be H+. So what we want to do is look at our A. What is A in both cases? Our purple A versus our red A. Can we come up with a name for that so I can stop calling them A's? It is the conjugate base. Why is it a conjugate base? So we can look at a couple options. It's the partner of our acid that we started with, so that means it must be a base. The other thing we could do is look at its structure. What charge does our conjugate base have?
Negative.
Negative. What species or negative species most often act as bases or nucleophiles because they have the ability to share those electrons. So we're looking at those as bases. Okay? if we're going to look at which of these two is the stronger acid, what we can go through and do is compare our purple to our red conjugate base. The one that can minimize that charge does what to the acidity of the corresponding conjugate acid? Okay, so let's put in some examples. Our top case, let's say A is an oxygen. In our bottom case, let's say our A is a carbon. Which acid is stronger, purple or red? Purple. We just saw that answer. Why is purple the stronger acid? Oxygen's more electronegative. That doesn't fix our side that minimizes charge. If it's more electronegative, it wants to hold that negative charge, meaning it can stabilize it. It's minimizing the effective charge. Carbon can't minimize that effective charge, and so it ends up being a less stable negative. Well, if the negative is less stable, will it form? If it's not going to form, what does that say about H+? The only way we can get our red A is if we form our H+. If we just said the red A does not form, what does that mean about our H+? Also does not form, which means, does our red HA act as an acid? No, it can't, because the products that it generates are unstable. They do not work. So when looking at ranking acidity, okay, or ranking acid strength, it's usually very helpful to draw out a reaction and evaluate the stability of the conjugate base. If that species can stabilize the negative charge, then we're looking at a strong acid to start. Okay, so it involves going back and forth across the reaction arrow. Yes?
Can you repeat again why it doesn't form?
Okay. So what we're doing, and it's ultimately a comparison. We have to compare. Everything we're dealing with are weak acids. So we're comparing O- to C-. Okay, because we're trying to decide which of those is more acidic, our purple or our red. Okay. Which of those is more stable? The top one, which means the less stable one is our red. Okay. So comparatively, we're saying the red one does not form because it's less stable in comparison to our purple one. If our red A- can't form, can we get our red H+? Nope. Which means what about our red HA? It's not going to dissociate. It's a weaker acid than our purple. Okay, does that make a little more sense? Okay. So what we just went through and did is a generic version of it. What if we'd asked instead for bases? Okay, which one's our strongest base? Why is the red one our strongest base? So in the case of our base, we're now looking at our reverse reaction. So I'm going to erase all of that. If we looked at O- going into our HO, yes, those are not proper structures. Going into our HC. Okay, which one's going to be the stronger base? I did swap the colors on you, didn't I? Sorry.
Aside from the obvious process of elimination,
Our purple one is going to be the stronger base. Why is the purple one our stronger base?
It's not stable in its current state.
What is the definition of a base? Proton acceptor. We don't see any protons in this, so that makes it a little bit more difficult. Okay, we could go through and add the proton. Is it going to be helpful to look at the ability of each of these to accept a proton? Why not?
Because they both count.
They both accept a proton. So we aren't going to be concerned about the proton aspect of this. What do we need to be concerned about? The electrons. And for it to be a strong base, what does it need to do?
Donate electrons.
Donate electrons, which means what about the energy of those electrons? High or low energy? The highest energy possible so that they can be shared with something else. So when we look at bases, we end up flipping the concept on it. What we want to do is see which one of these negatives does not want to be negative. Which one does not want to be negative? Carbon, because it's not very electronegative. So when we're ranking our acids and bases, we have to be careful on what we're looking at and adjust based on the definitions. Our acids, we're looking at trying to get rid of a hydrogen. So typically when we evaluate our acid strengths, we draw out the conjugate base and find whichever one's the most stable. Okay? Because the weaker the base, the stronger the acid. When we look at our base strength, we could go through and evaluate our conjugate acids. I typically find that more difficult. Why would I find that more difficult to look at the conjugate acids? Well, my overarching concept is what? Minimize charge. If I look at the conjugate acid, what's the charge in case of my bases? Neutral. I don't have anything to compare. So I want to instead look at the base themselves. Whichever one has the highest energy charge or the least stable is going to be the most basic. So I don't have to do a back and forth in that situation because I'm already starting in that charged state. Okay? Kind of makes sense? At least sort of. Okay. So let's come up with some rules. Some of these rules, hopefully the first 4 should look familiar to you. I've crossed out Rule 3 and Rule 4 because ultimately all those are our memorization tools from general chemistry. As opposed to explaining it to you, they just make you memorize some extra rules. So Rule 5 is ultimately, or sorry, Rule 6 is ultimately a discussion of Rule 3 and 4. So when trying to rank acidity, we want to start with Rule 1. Okay? In all cases, we are finding our biggest difference. Where that difference is now what we need to compare. Okay? So rule number 1, across a row, stronger acids have higher electronegativity. Okay? So if we compared, let's see, is this going to work? Yeah, we can do this. And again, I'm not going to balance out the charge on this, but let's say H bonded to O versus H bonded to F. Which one's the stronger acid? HF, what's the name for HF? Hydrofluoric acid versus our HO, we're probably looking at water. Which one's the acid? The one that we call an acid. Okay. Why is HF the stronger acid? Fluorine is more electronegative than the oxygen. It draws that the electron density away from our hydrogen, and we're looking at it being more acidic. Okay? We could go through and look at the stability of the conjugate base. So we'd be comparing F minus versus O minus. Which one can stabilize that negative charge better? Fluorine or oxygen? Fluorine, because it's more electronegative than our oxygen. If our conjugate base is more stable, what does that say about the acid? The acid becomes more acidic. Okay. Rule number 2, down a column, stronger acids have larger conjugate bases. All right, sounds a bit odd, but what we're comparing in that case would be something along the lines of HF, and let's run with HCl. Okay, which is the stronger acid? Hopefully you've got this one memorized. HCl is defined as a strong acid. What is HF? Not a strong acid. So which one's our stronger acid? HCl. If we run with what we used for our first rule, we'd go based on electronegativity. Which is our most electronegative element? Fluorine. Which would suggest which is the strongest acid? HF. Which isn't the case. So there's a competing factor that goes along with this. It's not just electronegativity. That competing factor has to do with size. Since I don't have the space on the iPad, we'll just draw it up on the board. We talked about this one already. What we're going to compare is F minus. So we put in those charges. F minus, how big is fluorine? Pretty small, really high up on our periodic table. So let's go extremes. Here's fluorine. Okay. Chlorine, where's chlorine? Below it, what happens when we move down a column? It gets bigger. We're putting our electrons in a higher energy state. So let's push it to the extreme. There's our chlorine. For it to be F minus or Cl minus, what has to happen? It has to gain an electron. Does an electron change its size depending on what atom has it? No, electrons are always the same size. So here's an electron in fluorine, here's an electron in chlorine. Whoops, I made it look bigger. Man, it's not getting any better. Okay, we've done this analogy before. Why do we minimize charge? Charge is dangerous, right? Bad, high energy. We want to minimize that charge as much as possible. Remember, don't stick your finger in the electrical outlet. If we have that charge, it's going to shock us. If you have to stick your hand into one of these, which one do you stick your hand into preferentially? Chlorine, because less likely to hit that electron, okay, that high energy electron. Why? It's spread over a much larger area. It's delocalized. Okay? If we can spread that charge density over a larger area, we decrease the energy and it becomes much more stable. Okay? Resonance is the prime example of that. So when we're looking at our acidities, we want to look at size as well as electronegativity. But what happens, like we had in that previous case, where our charge is held on the exact same type of atom, oxygen. There's now no difference across the row because oxygen is in the exact same position in the row as oxygen. Within a column, oxygen is in the exact same position as oxygen. So we have to move to a different set of rules. Those different set of rules are just refining it a little bit further. So we move to the next atom and evaluate the next atom, ultimately based on these kind of concepts. Why do we not look at size when we look at the next atom? So size disappears from the argument, and now it's only based on electronegativity. We're looking at putting the electron, our reactive electron, on that atom. If we don't have resonance, I cannot move that electron onto that larger atom, which means the charge always stays on our smaller atom. We cannot look at a size effect when we move to the next atom out. Right? It has to be based on electronegativity. So we get two rules that come out of that. Resonance, which is physically moving the electrons. Okay? Typically a little bit easier to see because you've taken that charge and you've put it somewhere else. And I'll draw out a perfect example of resonance, our classic example. Okay? If we can't physically move the electrons, but we have a difference in electronegativity next door, what we're looking at is the inductive effect. Okay? The ability of other atoms to withdraw that electron density. Okay? Questions about any of that? Should we look at some examples?
Yes.
Okay, before I get you completely going with those, and then I'm going to ditch you for a little bit because it's going to be a really long 45 minutes otherwise. This last one down here, I want to get you the structure for that. Okay. Whenever you see COOH, that should lead you to one conclusion. That is this functional group. What functional group is that? Carboxylic acid. How acidic is that? That's pretty acidic. Okay, it really depends what we're comparing it to. Okay, but that will be an acidic functional group. So we might expect our carboxylic acids, if we're trying to rank something, on the higher end of our acidity. Why are carboxylic acids more acidic? Okay, we looked at that electron withdrawing effect, right? Okay, we looked at ultimately an inductive effect. So we can draw out our conjugate base. Okay, and I left off all the lone pairs. Told you I wouldn't do that. Sorry. We remove that hydrogen, this is what we end up with. Agreed? Why would I remove the hydrogen from the oxygen, not from the carbon?
Easier to give up.
Why?
The electron density is being pulled towards the carbon atom.
Easier. Go to our charges. Our very first rule is electronegativity. Which atom is going to be easier to pull the electron density from that hydrogen? Oxygen, because oxygen is more electronegative than the carbon. So we would expect our acidic hydrogen to be the one on the end. And when we went through and evaluated the acidity of that, okay, we decided to balance that based on looking at an inductive effect. Is there another effect? Say yes. Yes. It's everybody's organics, 4-letter word. It's not 4 letters. We're looking at resonance. Where's our resonance structure in this? Anytime you find electrons, you should try and do resonance. There's 2 places that you can pull electrons from. Where are those 2 places when dealing with resonance? Pi bonds and lone pairs. Why pi bonds? They are much higher in energy. Why lone pairs? They're not involved in a bond now, so we could try and move them around and put them into a bond. All right, so what we could go through and do is attempt to move those electrons. Okay? If we take a look at our oxygen at the end, there's really only one place we can move it. Why is there only one place we can move those electrons? There's only one bond. Okay? I can't move those electrons anywhere else because there's no other bond to move them to. So we'll move the electrons towards our carbon. Okay, so what we've done is now put 2 more electrons between the carbon and the oxygen. What kind of bond do we have there? Pi bond. So when we're dealing with resonance, we're moving our lone pairs and we're making or breaking pi bonds. How many electrons would be around the carbon? How many electrons around it in black right now? 8 electrons. If we use the red arrow, we're moving 2 more in, so how many electrons would be around it? 10. Can carbon have 10 electrons? No. So the octet is not satisfied. This does not mean we don't have resonance. What this means is we now have to look at our structure and decide, is there some place I can move electrons? Okay, I need to get rid of 2 electrons around that carbon. The only electrons that we can move are pi bonds or lone pairs. Does our carbon have any lone pairs? Nope, so we can't touch those. Do we have a pi bond? How many pi bonds do we have? There's 2 because we just moved that red one in. Okay. Which pi bond do we decide to mess with? How about the one that we haven't dealt with yet? If we deal with the red one and move those electrons back, all right, well, we didn't draw a resonance structure. So let's see if we can push it somewhere else. So we want to take the electrons in our other pi bond and put them where? Why should they go to the oxygen? A couple good answers. It's more electronegative than the carbon, so it should absolutely take the electrons. What's the other big reason? Why did we move to trying to move electrons around that carbon anyway? It had too many electrons. So if we're going to break a pi bond, we'd better move those electrons away from the atom that was exceeding its octet. What's the net result? So if we drew this out, we'd have carbon, hydrogen we didn't touch, so we should draw it on there. Didn't touch those lone pairs. We have a new pi bond that was formed, and our other oxygen has a lone pair. We go through and evaluate formal charge, and you'll notice that top oxygen has a negative charge. Why does that make this structure, our initial one, more acidic? Well, we look to our conjugate base, and what do we do to determine if our acid is acidic? We want to see the stability of our conjugate base. What makes a conjugate base more stable? True, well, let's go less into the strict answer. Minimizing the charge. How can we minimize the charge? We want to spread that charge over as large an area as possible. What does resonance do? Neither of those structures are correct, right? We have to use them both. So if we look at the effective charge on that oxygen atom, in one structure it's -1, in the other structure it's 0. We spread that charge across two structures. What's the effective charge on that oxygen? -0.5, as opposed to a -1. We've made that oxygen atom more neutral, less charged, better off. Okay? So resonance does play an important role. That's the only one within these structures that deals with resonance. The rest of them you should be able to identify based on electronegativity and size. So I'm going to go ahead and erase most of what we've got drawn up there and let you talk with the people around you. Raise your hand if you've got questions and try and go through and rank these according to their acidity. So hopefully you guys have nailed down those first three. I don't remember the actual rule numbering, so I'm just writing the rules. So our first one is based on size. Our second one is an inductive effect, which I think was the last one on that list. Then we've got electronegativity. And then what do we have? And this one is an inductive. This is one that gets a little bit more complicated. Why is that one a little bit more complicated than the others? Not only are there 2 electronegative atoms, but it might also help to draw out the structure. Okay? So the one right above it might help to draw out a structure as well, but it was kind of okay. You could probably approximate that one pretty quickly. If you draw out the structure for these two, got our fluorine and our 3 hydrogens versus, where's our charge going to be held? If we look at the conjugate base,
It's going to be on the carbon.
the carbon takes the charge. We're removing that hydrogen and putting our lone pair on that carbon. There's our negative charge. So we can't use a size or electronegativity effect because it's the same atom that's holding the charge. So now what we can do is move to the next atom away, okay, and look at the electronegativity there. And in that case, we now have 2 fluorines versus 1 fluorine. The 2 fluorines more electron withdrawing. Okay? So we would expect that bottom structure to be more acidic, okay, or the more stable conjugate base. Okay? Questions on that one? How about the last sequence, putting them all together? How do we go through and process that last one? What's that?
Using multiple rules.
You're going to use multiple rules, but then how do you process this? Okay, simplify. Pick 2. Which 2? Doesn't matter. Pick 2. Any 2 you want and start the ranking process. Okay? Simplify. Don't try and rank them all at the exact same instant. Pick any 2 and get them nailed down first and then start to apply. Okay? Personally, I would probably have picked the first 2 just because I naturally read left to right. Maybe you're different. Okay? And I would take a look and say HCl is the stronger acid than H2O. Okay? How about CH3F? So what do I want to compare that to?
To HCl.
I want to compare that to either HCl or water. Why to those 2 and not to the last one? Because I've already built a ranking system. Stick within that system. So CH3F to HCl, which one's the stronger acid? HCl is the stronger acid. Okay? Why? A couple things that we could look at. Number 1, we could go back to our Lewis structures and compare where the charge is held. Where's that charge held? Carbon versus chlorine. Okay? Deciding that they're not in the same row or in the same column. So how can we compare those? Okay? Remember our size rules when they're in the same column. They're not in the same column. How can we compare them? Electronegativity only works when we're in the same row. They're also not in the same row. How do we compare these? We could make a hand-wavy argument with the conjugate base. Is there something that they have in common? Is there a middle ground? At least 3 of you in the back should be able to answer this question. What's that middle ground? Fluorine. Compare them to HF. HF versus HCl, which one's the stronger acid? HCl. Within a column. HCl is the stronger acid. HF versus CH, or carbon CH. Which one's the stronger acid? HF. They're now within a row, right? HF is the stronger acid over our carbon, but it's weaker than HCl. Where does that put our CH structure? Weaker than HCl. Find the common denominator. Our periodic tables are in here for a reason. Every exam is going to have a modified periodic table on the front of it. I will post that cover page so you guys have access to that before the exam. Okay? So try and find that simple comparison. Okay? What's the next issue? That puts our CHF3 less than our HCl. Now we have to compare it to our water. Okay, where is it relative to our water? What atom holds the charge in water? What atom holds the charge in CH3F? Carbon. Which one can hold the charge better? Oxygen, which makes the oxygen more acidic, our stronger acid. We put our CH3F after our water. Evaluate where your charge sits. Okay, and this is what you have to be very careful with when you go through and approach these. How about that last one? We can most easily zoom in on our oxygen, but we could start with that chlorine. We could go through and do our same comparisons that we did before. Okay, with the charge, negative charge on chlorine versus oxygen. We did a comparison already. Okay, HCl is a strong acid. Carboxylic acids are stronger, but they are not strong acids. Okay, strong acids carry a very specific meaning. We could then compare it to our water. What's the difference between our carboxylic acid and our water? All sorts of arguments we can come up with here. Can look at an inductive effect or a resonance effect. Okay, to suggest that that one is more acidic. Okay? Questions about that? When are we done? 12:30? Okay. Going through and ranking your acids and bases is a very common question. Acid and base chemistry shows up all over the place. You spent, and theoretically, a year already on acids and bases. And in that year, hopefully you had some experience with ranking these kinds of things so that you're not trying to play catch up at this point. Okay? We will keep coming back to acid and base strength, and it's going to keep coming back to those previous rules. Okay? Minimize that charge and do whatever you can do within that structure to stabilize it. Okay? Questions about ranking your acid strengths? Yes?
When you say larger conjugate base, you're only referring to the atom holding the charge, not the
Only the atom holding the charge. Our first 2 rules only apply to the atom holding the charge. Okay? If we cannot find a difference, then we can move further away. At that point, those atoms are not holding the charge. We cannot do a comparison on size. Size only works when we're looking at where the electron is located. If the electron is not physically on that atom, we cannot do a size comparison. Okay? The equivalent analysis to size is our resonance, because that's when you can physically move it. Okay? And even then, you're not really doing a size argument. You're saying you're putting that charge somewhere else. Okay? Other questions? Okay. Oh, just did those. Can we quantify this? So if we're given a reaction and asked to predict the products. Okay? So you will see this in sapling, and you'll see it in your exams as well. If you're given two species, so in this case, I'm going to not name those, just call them A and B. We got structure A and B, and we want to decide A and B was a bad idea, because that's acid and base. 1 and 2. If we want to go through and decide how that reaction occurs, which one acts as the acid, which one acts as the base. Okay? A couple approaches. Number one, which everybody will probably hate, is you go through and you draw all your possible products. Okay? So in our first line, what do we have? Structure 1 acted as an acid. How do you know it acted as an acid? When we look at the conjugate of 1, it's lost that hydrogen. Okay? So that means that it initially had to act as an acid. If it acts as an acid, what did 2 act as? The base. And the second example, what happened? So look to our products. If we look at our conjugate of 1, it accepted a hydrogen, which means in our first case it acted, or our second case, it acted as a base, which means water acted as our acid. How do we decide which one's correct? We want to look for our charges, look for stability. We have two choices, because we have a positive and we have a negative. Right? Organic chemistry is looking at the motion of electrons. Which charge do you think we'll evaluate? The negative, because that's where we're saying we have electrons. So we could look at those two products and try and decide which one of those is more stable. So let me go through and circle them both. Got the top one circled, bottom one now circled. Which one of those negatives is more stable? Top one, because we've got an induction argument. We also have a resonance argument. What does that mean? If we had to choose between these two situations, this top one is the most likely, this other one more likely to do the reverse. Right? We've now gone through, based on understanding our definitions of acids and bases, predicted what our possible products were. And we now have those two products to work with. Right? Could we quantify this? Yeah, we quantify it using, we could use the KAs. Typically when we look at our KAs, anybody know the size of our KAs? We're looking at our weak acids. Ka is something like 2.3 times 10 to the minus 4. Anybody happy with that number? Most people don't like that. Why? We got scientific notation. We also have a negative sign floating through there, all ripe for mistakes. Right? Again, think simplicity. If we need to tell our kids something about these compounds, telling them a Ka value, they barely understand how to count to 10 on their hands. Throwing in an exponent with a negative value, right, it's going to make it really difficult. So what do we convert it to? We go to pKas. So we take the negative log of our Ka to generate our pKa. And if we go through and look at our pKa, what does it end up equaling? For that same number, we're looking... Anybody have a calculator? I didn't want you to pull out a calculator. I just didn't want someone to prove me wrong. And you pull out the calculator anyway. Thanks. 4.2 might actually be lower. It might be closer to the 3. Okay, but we're going to be sitting somewhere around that 4 value. Okay. What does that mean? If we looked at a strong acid, what's the size of our Ka? Our strong acids have massive Kas. We're looking at 1 times 10 to the 23rd. Why not? Okay. Massive. we have no reactants. Remember when you look at products over reactants, if you have virtually no reactants, what are we doing? We're dividing by an infinitely small number. We get an infinitely large number as a result. What happens to the pKa? For our strong acids, our pKa's tend to be really, really small. Well, it's not smaller. They're so small they go negative. So the stronger our acid, the smaller the number. For organic chemistry, most of our pKa's are going to be sitting in that probably 4 range is our lowest acidity. And we'll push all the way up to, as far as reactivity, as far as acids go, up to the pKa of 15.7, which is the pKa of water or alcohol functional groups. So one of the things that can help when looking at reactivity within organic chemistry is not only have your functional groups memorized, but spend some time to memorize some pKa's for those functional groups. So if you see an alcohol functional group and you're expected to predict a reaction, well, the alcohol functional group is relatively not acidic because it has a pKa of something like 15.7. You now have a way of saying, oh, that's not going to act as an acid. Okay, so you can do some kind of predictive ability if you know those pKa's. So I highly recommend that on top of your functional group list, you go through and you spend some time to memorize some pKa's. That said, how many pKa's did I memorize when I took organic chemistry?
0.
Absolutely none. So it's not critical to memorize them, but there were plenty of times during an exam I'd look at a problem and be like, oh, if I just knew the pKa. Okay, so it can really help when you go through and predict these things. Okay? So we're looking at charge and reactivity. So if we now push this a little bit further and we want to decide this is our correct equation, which side of the reaction is favored? Do I expect reactants or products? Why would I ever want to know which side of the reaction is favored in a chemistry class? Not even that I know what to expect. When we go into lab and we mix some chemicals, do we sit there and observe that nothing happens? How exciting would your experiments be? You walk into lab, every single experiment, you mix them together and nothing happens. That proves something. It proved the lack of a reaction. That's kind of interesting. Most people don't like those results. Okay? I would argue it actually makes it more difficult. Okay? We want to see a result. So if we can go through and predict which side of the reaction is favored before we even mix the reagents, we could actually start to decide what we would do before we get into the lab, as opposed to just randomly mixing stuff. So how could we go through and decide that? Painfully, that's right. We can go through and compare pKa's. Okay? The pKa represents what? The acidity. So what we can go through with this equation, and we're going to try and decide which side of the reaction is favored. Okay, so in that last example, all we said was that first one, it should act as an acid. That was it. We didn't actually predict that it would react. We just said that our benzoic acid, our first structure, should act as an acid. Now what we want to decide is, will it react at all? Okay, to do that, we can use our pKa's. I know I just told you to do this, but I figured some of you are already looking at tables. What's the pKa of a benzoic acid? Oh, you didn't do that? Okay.
-7.
Your pKa for benzoic acids tend to fall about 4. Okay? So when I said our acid strengths, pKa's for our carboxylic acids are 4. They're the most acidic functional group that we're going to be dealing with. So we're sitting right around that 4 range. What I want to do is be able to compare this to another acid. Where's my other acid? I will go to the product side and look at the acidity for that. What's the pKa for H3O+? Roughly negative 1.5, which I might be making up, but it's negative. Okay? How can we use that? It's the stronger acid. So this is something, and it's not very nice, but it's something that's worked for me fairly commonly. If I'm trying to decide which way my reaction is going to lie, and I know something about the acidity of these, what I'm going to do is what's called a face test. And I'm saying, okay, I've got these two solutions. I don't have a choice. One of them is getting splashed in my face. Which one would I prefer to have splashed in my face? I want the weakest one. Because the strongest one I know is going to hurt. Okay? But the weakest one, maybe I can get away unscathed. Chemistry does the same thing. It's going to strive for the side of the reaction that generates the weakest acid. Okay? Why? Your weakest acids are less reactive, lower in charge, lower in energy. Okay? So which side of the reaction generates the weakest acid? Sorry, you're all pointing. That doesn't work for me. We're going to the left. So if we had to decide what happened to benzoic acid when we add it to water, say nothing. Its structure stays the same. Really important process for when we move into the lab in just a couple minutes here. All right? So if I want benzoic acid to act as an acid, I need to react it with a stronger base than water. Water's not good enough to get me enough of that transition. All right? Why would I want to change its structure? What else changes with the structure? Could look at reactivity. I'd say there's something even easier. The intermolecular forces. The intermolecular forces change. What happens to your melting point? Changes. What happens to your solubility? Changes. I can take advantage of this acid-base characteristics to cause my compound to change its solubility. Why is that important? Acid-base chemistry is reversible, easily reversible. So I could go through and add an acid to make it now my conjugate acid, or I could add a base to remove it and send it back the other direction. So if we take a look at our solubility for this compound, yes, we have hydrogen bonding out here, but we have a lot more London dispersion forces, which means the solubility of this compound is insoluble in water. What happens when I move to the product side? Still roughly the same size, but what happened to the strength of our red intermolecular forces? We went from hydrogen bonding to ionic. We have that negative charge on that oxygen. There's an ionic interaction. What compounds are ionic? Okay. General compound that's probably in all of your food. It's ionic. Salt. What can you tell me about the solubility of salts? They completely dissociate. They are water soluble. By running a simple acid-base reaction, I can take benzoic acid from an organic phase and I can transfer it into an aqueous phase. Just as easily, I can take it from that aqueous phase and back into the organic phase by just changing the amount of acid present, the acid or base. Okay? Pretty important. So, our lesson on that, small pKa's are stronger acids. Our reactions are going to favor the side with the biggest pKa, so the weakest acid. Okay? Arrows. Ooh. We'll talk about arrows a little bit more when we keep talking about them or when we see them again. Make sure you're aware of what the definition is on each of your arrows and when to use them. So you've got your equilibrium, your reaction, your resonance, mechanistic arrows, which we haven't talked about yet, but we will see those in a little while. Know what they mean and when to use them appropriately. Definitions, massively, wickedly, stupidly important. You will be required to know these definitions. I guarantee I will ask a strict definition question on acids and bases on every single exam. Right? Taken further, you will see those definitions applied on every single exam. So make sure you know those definitions. And where we'll pick up on Wednesday is doing some predictions about acid-base characteristics with our functional groups, and then taking it further into Chapter 4. I should get the Chapter 4 slides up, at least in part.